Good morning, everyone. Welcome to the lecture series of Microprocessor. And in this lecture, this is the third lecture of my video. And in this lecture, we are going to study the pin diagram of 8086. So this topic is related to the course Microprocessor with the subject code KCS 403, and the students of CSC branch, Computer Science branch, they are studying, and the related branches, they are studying this subject in second year, fourth semester as per AKGEC. So pin diagram and the description of 8086 microprocessor. First thing, we must understand that your 8085 was your 8-bit processor, and 8086 is a 16-bit processor, which is manufactured by the Intel in 1978. And like the pin configuration of 8085 microprocessor, the 8086 microprocessor also contain 40 pin IC, and we have dual inline package. So your 8086 is a 16-bit microprocessor, which states that we whatever data we want to process, that will be of 16-bit, and to process the 16-bit data we must have 16-bit address lines, right? So accumulator will be of 16-bit, registers will be of 16-bit. So however, unlike the 8085 microprocessor, the 8086 have a better performance, and if it operates in two hardware mode. One is your minimum mode and the second one is maximum mode. The minimum mode is a single processor configuration, whereas the maximum mode is multiple processor configuration, when we want to communicate with the multiple processors, right? And in case of minimum mode, all the control signals will be generated by the 8086, but in case of maximum mode, some of the control signal will be generated by the coprocessor, which are used during the communication. And due to this reason, in the 40 pin IC, the 8 pins, that is from pin number 24 to 32, that we'll see in the later slides, they are assigned some different configuration separately, and according to the mode, first we have to select the mode, and then according to that your pins will be working. And we will discuss the pin description in this section, but before that, we let us have a look diagram of 8086. And before this is the pin diagram of 8086. Before starting the pin diagram, let us check the features of 8086 first. So 8086, it is a 16-bit. It is a 16-bit microprocessor. So it states that with the help of 2 raised to the power 16, that is 1 megabyte memory can be accessed. Sorry, it is a 16-bit microprocessor, and we have 20 address lines. We have 20 address lines, and with the help of 20 address lines, 2 raised to the power 20, that is 1 MB, 1 megabyte memory we can access. And we have 16-bit microprocessor, which states that we have 16 data lines, right? So this 1 MB memory is divided into a few segments. Your complete memory is divided into few segments that are named as code segment, data segment, extra segment, and stack segment. We are not going to discuss these segments in this lecture. We may have some dedicated lecture on the memory segmentation, and we must remember that each segment will be of 64 kilobyte max, right? Each segment will be having 64 kilobyte. And then your 8086 comes into hardware mode. That we have seen in the previous slide, that is minimum mode. And maximum mode. Then we have 2 memory banks are there. which are named as even memory bank and odd memory bank. This complete 1 megabyte memory is classified into two parts of 512 KB and 512 KB, right? So this is classified into two memory banks because we know that in 8086 we have 2 bytes to be accessed, and on data we have in the locations we have 1 byte which will be stored. So in one machine cycle 2 bytes will be accessed simultaneously. So these bytes, when these bytes should be accessed in a consecutive way. So one byte should be taken from the even bank and the another byte should be taken from the odd bank. In even memory bank, we will have the addresses. We will have all the even addresses, 4H, and it will go up to F, 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 E, H. And in case of odd memory bank, we are going to have the all addresses. All the odd addresses are collected in this odd bank, and it will go up to it will go up to finally, right? This even memory bank will be selected whenever the value of A0 signal is 0, and this odd memory bank will be selected whenever the value of bus high enable signal bar is 0, right? So these two signals are used to select the memory bank. So this even, we know that we start the counting from even from 0, 1, 2, 3. So your even memory bank is used to store lower byte data, and this odd memory bank is used to store higher byte of the data. Whatever the 16-bit data, we have this 16-bit data complete. (16-bit data or address, whatever we have. So we have this higher byte and lower byte. Okay, your lower byte will be stored in even address, higher byte will be stored in odd address. So this way, so whenever we write the instruction in 8086, whenever we start writing the program in 8086, we will start from the even address, so that it can be executed like this, from 0 location to 1 location, then 2 to 3 location. This way it will be executed. So let us quickly check the pin diagram of 8086. In 8086 microprocessor, it has a 40 pin IC, but a few separated pin configuration for minimum and maximum mode. So in this pin diagram, we can see that your pin number 1 is VSS. From pin number 2 to pin number 16 and pin number 39. These pins are multiplexed address lines and data lines, right? So we have multiplexed address lines and data lines. These lines can be extracted with the help of this ALE pin, which is connected at pin number 25. In the later slides, we will see how these pins can be extracted. Then pin number 17 is non-maskable interrupt. Then we have interrupt clock, that is clock signal, which is used for the synchronization purpose. In 8086, we have two ground pin at pin number 1 and pin number 20, so that we can have a better functionality. Then pin number 21, we have the reset. Then 22 ready bar, 23 test bar, 24 here we have test bar, 24 and 25 are QS1 and QS2. So these pins from pin number 24 to 31, if you are working in maximum mode, means the value at this pin number 33 is 1. It is connected to VCC. Your 8086 will work in maximum mode, and these pins will be used. and when this pin is connected to ground and your 8086 works in minimum mode, these pins hold HLDA. This right side pins will be connected to 8086. Similarly, we have the address buses which are connected, which are multiplexed with status signals. So please make one correction here, that we don't have here multiplexed address lines. We have only A16, A17, A18, A19. So let us check the working of each pin. VCC, which is present at pin number 40. At this pin, your external power supply, that is 5 volt, will be connected, which is necessary for the working of any IC. Then VSS pin number 1 and pin number 20, we have 2 ground pin in 8086 microprocessor, so that we can have a better, we can have a less power dissipation. Then from pin number 2 to 16 and pin number 39, we have this multiplexed AD0 to AD15. We have these multiplexed lines, and out of 20 address lines, 16 lines are multiplexed with data lines, and rest of the 4 lines are multiplexed with status line, right? So these pins will be extracted with the help of ALE signal. When the value of ALE signal is 1, when the value of ALE signal is 1, we will have address on AD0 to AD15, and when the value of ALE signal is 0, we have data on these lines, right? So these can be extracted with the help of ALE signal. Just a minute. Then we have the A16, A17, A18 and A19. Rest 4 address lines which are multiplexed with S3, S4, S5 and S6, right? So these are connected to pin number 35 to 38, right? So out of 20 address lines, 16 address lines are connected with data lines, and rest 4 address lines are multiplexed with status signals. So these are also multiplexed form with the help with the status signal, and this case your memory operation, these pin act as a address bus and contain the memory address of any particular instruction. And however, from the IO operation, these pins are low, that shows that the status of the processor. So out of these 4 status signal, S3 and S4 are used to select the segment. So this is the segment table. So S3 and S4 are used to tell the status of the segment. So if you have 0, 0, S4 is 0, S3 is 0, we use extra segment. Then for 0, 1, we use stack segment. For 1, 0, when the value of S3 is 1, the value of S4 is 0, we use code segment. And for 1, 1, we use data segment. S5 is used by the microprocessor to, it will tell you the contents of interrupt flag, that with, if the value of interrupt flag is 1, means your interrupt signals are enabled, and when the value of interrupt flag is 0, means all the interrupts are disabled. So S5 will tell you the status of the interrupt flag. S6 is connected to the, is always connected to it is always connected to 0. So when it is 0, it present as the signal at this pin. It indicates that 8086 is holding the access of the buses, otherwise it will be high. Then we have bus high enable pin, which is multiplexed with S7, which is present at pin number 34. We know that this BHE pin, I have told you that bus high enable pin, which is used to select the memory bank. Now whether we want to read from the upper byte or lower byte, or we want to read the complete word, so that will be done with the pin number 34. So we have this combination. If the value of BHE pin is 0, S7 is 0, all 16 bits will be accessed For 0, 1 upper byte will be accessed, for 1, 0 lower byte will be accessed, and for 1, 1 nothing will be done. Then we have minimum / maximum mode, which is connected at pin number 33. The status at this particular pin will decide in which hardware mode your 8086 will be working. So when the so when the value at this pin minimum / maximum bar is 0, it is 0, your device will work in maximum mode, and when the value of this pin minimum / maximum bar is 1, your 8085 will work in 8086 will work in minimum mode, right? So this way we can select the minimum and maximum mode. Then we have read bar pin, which is connected to pin number 32. It is an active low signal which indicates that, so whenever the value of read bar signal is 0, it states that your microprocessor wants to read some data from memory or some IO devices. Then we have clock, which is connected at pin number 19. So pin number 19 is clock, which is this clock signal is present at pin number 19, so that they can provide the timing to the internal operation. We can have the synchronization process between the internal processes. So clock's frequency, which is generated, which is used by 8086 is 5 megahertz, 8 megahertz and 10 megahertz. So depending upon the version, 8086 is using 5 megahertz, 8086 version 1 is using 8 megahertz, 8086 version 2 is using 10 megahertz frequency, right? So depending upon the frequency, depending upon the version, we can have the frequency, and the duty cycle of the clock is maintained at 33%. Duty cycle is maintained at 33%. Then we have non-maskable interrupt. Non-maskable interrupt, which is present at pin number 17. It is a edge triggered interrupt, and it cannot be postponed. And we have to execute that. Then we have test pin, which is connected at pin number 23. This pin is basically shows the wait instruction. So however a low signal is at this pin, this pin occurs, then the processing inside the microprocessor continues, as against in the case of high signal. This stands for interrupt request. The processor after each clock cycle samples the interrupt, and if the signal at this pin is found to be high, then the microprocessor controls the interrupt internally. And this INTR interrupt request is your level triggered interrupt. Then we have ready. This signal is used by the peripheral and the memory devices in order to show that readiness for the next operation, and this ready pin is used when we have the communication between the slow peripheral devices. Suppose you have the microprocessor which is working at 5 megahertz and you are communicating with the 3 megahertz frequency, right? So during that operation, some wait states will be inserted, and during that one pin lock pin also be used, because in the wait state no operation will be done, only the T states will be increased, so that they can match the speed with the another microprocessor. So microprocessor should be locked, and during that lock period, microprocessor should not execute any instruction, no operation will be done. Then reset, pin number 21 is reset. Whenever this pin is enabled, it reset the processor and the other devices connected to it. So whenever this reset pin is activated, the content of code segment, the contents of code segment will be initialized to Just a minute. The contents of code segment will be initialized to FFFFH, and with the code segment we have associated instruction pointer which works as an offset register, and the content of this instruction pointer will be initialized to 0000H. So the physical address which is calculated by the formula, that is segment address multiplied by 10H plus offset address. So it will be FFFFH multiplied by 10H plus 0000H. Right. So total address which is carried out by 20 address lines, this will be 0H. Right. So whenever your reset is executed, the microprocessor will start its execution from this address, and rest all the registers will be initialized to 0000H. Then we have interrupt acknowledgement. Now let us check the working of this 8086 in minimum mode and in maximum mode, right? So in minimum mode, the pin number 33 should be connected to VCC, right? So pin number 24 will be connected to interrupt acknowledgement. It is the acknowledgement signal which is sent whenever you have the interrupt request. Then we have ALA pin which is connected to pin number 25. That is address latch enable pin, which is used to extract the multiplex address line and data lines, or address lines and status lines, right? So this is done to inform the microprocessor and the memory devices about fetching of data or instruction at the memory or some IO location. Then we have data enable bar which is connected to pin number 26. It is data enable. This is an active low pin, which means that whenever it is 0 is present at this pin, then the transceiver gets enabled, and it separates the data from the multiplex address and data bus. Then we have DT/R bar which is connected at pin number 27. It is named as data transmission/reception bar. So when the value of this DT/R bar is 1, your data transmission will be done, and whenever the value at this pin is 0, your data reception will be done. Then we have memory/IO bar which is connected at pin number 28. This pin is used by the microprocessor when we have a choice that whether we want to work on memory or we want to work on IO devices. So if the value of this pin is 1, we are working on memory, we are reading or writing on memory, and whenever the value of this memory/IO bar is 0, we are going to access the IO devices. Then we have write bar, pin number 29, write bar. It is also active low signal. Whenever the value is 0, it states that we have sufficient data on data lines which can be written on memory or on output device. Then we have hold and HLDA. This pin number 30 and 31, they are used by the DMA, direct memory access. The DMA controller will send the hold signal to microprocessor. So microprocessor, and then microprocessor completes its current execution task and will release its address buses, data buses and control buses. So hold acknowledgement signal, in return to that hold acknowledgement signal will be sent by the microprocessor. So this pin is used as a response pin for the hold request. When the request for the accessing the bus is produced by the external entity, then the microprocessor acknowledge the device that your request will be considered once the current execution will be done. So once the current execution is done, microprocessor will send the hold acknowledgement signal, and which indicates that now my buses are free, my address buses, data buses and control buses, all my resources are free, you can use them. So Next, we have the operation in maximum mode. So from pin number 26 to 28, let us check the pin diagram once. This pin diagram from pin number, now for maximum mode, this pin should be connected to 0, and from pin number 24 to 31. Now we are going to study the function of these pins, because in maximum modes these request, grant, lock, S2, S1, S0, QS0 and QS1 will be used. So let us quickly check the working in maximum mode. So under this maximum mode, from pin number 26 to 28, we have the S2 bar, S1 bar and S0 bar. So depending upon the value, we can have the operation like we have interrupt acknowledgement for all zeros. For 000, we have interrupt acknowledgement. Then for 001, we are reading data from IO ports. For 010, we are writing data on IO ports. So when the value of S0 is 0, S1 is 1 and S2 is 1, we have halt operation. Then for 100, we are reading data from memory. From 110, we are writing data on memory, and for 111, nothing will be done. Your device will be in passive state, or we can say that your device will be in inactive mode. Next, we have the pin number 24 and 25, that is your QS1 and QS0, which is used by the 6-byte instruction queue. We know that your 8086 is the first microprocessor which introduced the pipelining, right? Pipelining states that whenever your instruction is executing, microprocessor fetch the instruction. Whenever the instruction is executed, on the back side of the operation, your microprocessor will collect the next instruction. Next instruction will be fetched and it will be stored in a queue, so that the time will be saved and the execution can be done in a parallel way, in a pipeline way. So these QS1 and QS2 will tell you the status of the queue. So when the values are 00, no operation will be done. For 01, first byte from the queue will be read. For 10, queue is empty. For 11, subsequent byte will be read. Then we have lock bar pin, that is pin number 29. This pin is provided in the maximum mode operation. So basically, when the single processor is using the buses or the resources of the 8086 and peripheral, then it locks the resources. It will lock the resources used by that, so that no other entity can access the resources until the recent process is completed. Then we have request grant 0 and request grant 1, which is connected to pin number 30 and 31. Now, due to the involvement of multiple processor, these pin indicates the request and grant permission for accessing the buses of 8086. Not only buses, they can send the request to access the memory and the peripheral devices also, right? So when both the signals are high, GT0 will have this pin, that is your pin number 30, will have the higher priority as compared to your pin number 31. Request which is connected at pin number 30, that will be executed first as compared to pin number 31, right? So this is all about the pin description of 8086. Thank you so much.